Okay, welcome to Balancing Equations. Ignore all the little gobbledygook on the screen. We're going to just focus in here. Balancing equations is as easy as making change, and that's the way you have to think about it. Let's suppose we live in a country where Spock is on all of our money, which would be really cool. Someone has a $10 bill, and you have toonies. Well, how are you two going to make change? Seems impossible to believe, but at one point in time you had trouble with this. You go, well, it's pretty obvious. I simply have to give my friend 5 toonies and I will have the same amount of money as this $10 bill, and you can make your exchange. Otherwise, one of you is getting ripped off. Little kids have tremendous trouble understanding this. I did as a child. When a store would give me change, and all I could think about was he had my 10 and I just had all these quarters and $1 and $2 bills because I'm that old. They weren't toonies and loonies. But you understand this. But all I have to do is change it a little bit and you get confused. Suppose we lived in a country that had toonies and threenies. There's actually been a good argument for $2 and $3 coins for making change a bit easier. So you and your friend get together. Your friend says, I need a toonie for the vending machine. All I have is threenies, and the vending machine doesn't take them. And your friend says, sure, no problem. Give me your threenie, I'll give you a toonie. It's like, yeah, but I just got ripped off. And so you say to your friend, you give me 2 toonies for my threenie. And your friend says, now I've been ripped off. So the question is, what is the solution here? Well, when do 3s and 2s land on the same number? So we start tossing more coins on the table. At this point, you have $6 on the left, $2 on the right. We go one more, and we have $9 on the left, $6 on the right. But if I go in here and remove this, now 2 threenies and 3 toonies are the same amount of money. So you literally just switch over what you get. So most of you, I think, could manage that. So let's take a look at one of the simplest reactions we've done. Setting fire to hydrogen powers most of our really good rockets. 2 hydrogen atoms show up with 2 oxygen atoms showing up, and they form a single water molecule. Do we have a mismatch? Sure, we have 2 hydrogens here, 2 oxygens here, but 1 oxygen has gone missing. Now, what does that look like? Let's look at it from a simple counting aspect. 2 hydrogens went in, and the 2 oxygen sisters, Oxina and Oxana, show up, and they want to have a date. They're planning to have a reaction. Well, what happens is Oxina walks off with 2 of the hydrogens, and her sister is left all by herself. This is a crying shame. Look at this. It's not right. We've lost an oxygen. If this is a child, you're in big trouble. But if these twin sisters, I've seen enough Victorian horror movies, this sister is going to come and kill everybody because she's going to be so upset. And she's going to haunt the mansion for decades afterwards. So we have to provide her a date. And not just 1, she needs 2. They're playas, you know what I'm saying? They insist on having 2 squires come along. So somehow we've got to get her a date as well. A double date. And we can turn that frown into a smile, right? She's only like sort of happy now. Actually, she kind of looks mental, like she's going to snap at any moment, but that's because she had to wait. So this would make her happy, but we don't have enough pairs of hydrogens coming in. So what we would have to do is add a second set of hydrogens. And now we can say, okay, 2 pairs of hydrogens. So let me see here, get a nice thick line. If we put in cooperate 2, oh, it's going to do that now, is it? 2, I'm not re-recording this video just over that. 2 pairs of hydrogens and 1 set of the oxygen sisters are capable of making 2 complete water molecules. I can't really fit it in there. I'll have to nudge it over a bit. So I'll go like this, give myself a bit of room, and then now I can draw in my 2. And it's balanced. So this is just slightly more complicated than the toonies and threenies. And the idea is to make Spock smile, if you get this right. Now here's the question. So many students want to change this little number here instead. They want to make that the 4. No. Once you've been provided the little numbers, you may not tamper with them ever again. You cannot get an H4. The reason you get an H2 is because each hydrogen shares 1 with its neighbor. And there's no way to do this with 4 of them. So this was already decided. This pairing showed up to begin with. And you cannot tamper with it. So you leave those small numbers alone because they're describing the assembled parts you are receiving. You stay out of this. I've got another example to show you how to do that. But anyway, here's the first introduction to balancing equations, and then I'm going to switch to handwritten, which is a lot easier to follow if I actually use your own worksheets. Now, imagine coming in and seeing this on the blackboard. What on earth have I been doing? This must be watched and participated in as a process. You can't look at the complete answers and learn it. So the textbook method is going to be really hard for you to do. And if you're gapping out while this is being taught, good luck. Because when you finally come up from your cell phone, you're going to see this mess on the screen or the board, and you will have no idea what's going on. If you participate along the way, like tying your shoelaces, it's easy to understand when you participate. If you just look at a lot of finished knots, I have no idea how that was done. Okay, so here's the first lesson on balancing.